let's review. If this thing's going to work, does it have to be a voltaic or an electrolytic cell?
It's going to work by itself?
Yeah.
Voltaic.
Why?
Oh, because it's spontaneous. It doesn't need energy to be put in.
Doesn't need energy. So what do you want the E naught value to be? A positive or a negative number? Positive. What do you want the Gibbs free energy sign to be? Negative. What do you want the K value to be?
Big.
Big. So all of these fit together. Big K, positive E naught, negative delta G. Okay? All three of those fit together in terms of saying a reaction is going to be spontaneous. Okay. So if you look at this reaction, and again, you're on the test, you're not going to have this full list of all the redox reactions like they used to give you. They're going to give you like a table that has part of it, and that's what's happening here. Now, if you look at these reactions, why do you know that first one, the O2 plus water, okay, using the hydroxide, why do you know that's going to stay in the direction that it's written?
O2 needs to be a reactant.
Yeah, and that's the only one that has O2 as a reactant. Okay, cool. So the first one's going to stay at 0.34. Now, what do you want to have happen in the second one? You want the zinc to show up as a reactant. But look at this. What's the only one that has zinc in it? You got to flip it. Because remember, this is redox reactions. Not re-re reactions, not ox-ox reactions. Okay?
Okay. No. It's been a while. Yeah. I don't know what's wrong with that.
Okay. Now, here's the advantage of flipping that second one. Mathematically, why does it work?
Positive.
You get a positive E naught value. Okay? It's cool. All right. Hey, that fits. And you can add them together to get the right equation. Now, what are you going to have to do with that second reaction? Flip the sign and
Add them together.
and how many electrons are in the first
2 and
one?
4, so you got to double it.
Yeah. Okay?
Yeah. My bad.
Wow.
My bad, bro.
That was it.
That was neat.
So you do all of that and you get 1.65 positive number, winner, winner, chicken dinner. Okay. Then it says on that second one, that second question, the electrolytic K on the diagram of the cell above, draw an arrow, indicate the direction of the migration of the hydroxide through the electrolytic. So here's the question. When you drew that, which direction is it going to move?
To the anode.
Huh?
Anode.
Why?
Oxidation.
Oxidation takes place at the anode. There you go. Now, then you get to B. Then it's like, as the cell operates, does the mass of the cell increase, decrease, or remain the same?
You tell me. I think it's increased.
Why?
Well, if you do it'll like get the actual equation, it's 2 zinc and oxygen yields 2 zinc oxide and water, and you're just combining the stuff, and then basically just increases.
Yeah, because you're taking zinc and you're reacting with oxygen, and you're making zinc oxide. Okay?
Wait, that's it.
That's all you have to say. Because you're making zinc oxide from zinc and oxygen. It's like if you take steel wool and burn it on a scale, the mass increases because it's reacting with oxygen in the air. We'll try that sometime. Okay. Now, to do C, you have to use the Nernst equation. Well, it's handy. Because on C, you've got zinc air is taken to the top of the mountain, the air pressure is lower. Will the cell potential be higher or lower than the same as the cell potential at lower elevation? So if you look at this in terms of the Nernst equation, you have E equals E naught minus 0.0592 over N times the log. Now, this one gets a little bit sketchy, mainly because of the fact that typically, it's your products over reactants, which is your ZNO, and then your concentration of your oxygen, okay? But typically, you really don't necessarily worry about the concentration of your ZNO because that's like a solid, okay?
What about the zinc?
But certainly not the zinc because that's just going to be sitting there. So you got to have something to talk about. So here's the story. So at a higher elevation, what's going to happen to the concentration of your oxygen molecule? That's the bigger story. The bigger story is that your oxygen is going to be, you're going to need a higher elevation. There's less pressure. So your oxygen is going to become less. So then if your oxygen becomes less, what's going to happen to the value of Q? It gets bigger, right? So remember, there's an inverse relationship between E and Q. So as Q gets bigger, E becomes smaller. And you could even, you didn't even necessarily have to have that if you just think it through. Like, oh, we're reacting this with oxygen. At a higher altitude, there's less oxygen. So you got it, because if your oxygen concentration goes to zero, the cell is going to stop anyway. I mean, if you just kind of think it through that way.
They take that.
All right, so stoic to the rescue on D. Lightweight metals in order to transfer more electrons with smaller mass, sodium, calcium being investigated. So which one are you going to pick? The calcium or the sodium?
I said calcium, but I didn't do this whole.
Why?
I just talked about atomic radius, but is that like nothing to do with?
Oh, it does, but that isn't the point of the story.
Oh, okay, my bad.
Look at it this way. If you have 1 gram of sodium, and you divide that by the molar mass, 1 mole, you get 0.043 moles of sodium. Well, what's the charge on a sodium ion? 1 plus, okay? So that means that could also give up that many moles of electron, right? Cool with that. Now, you also have 1 gram of calcium, okay? Now, calcium has a bigger molar mass, and you get 0.0250 moles of calcium. But, yeah, for every 1 mole of calcium, you get 2 moles of electrons. And you do that, you get 0.05 moles of electron. So your calcium is actually better.
Oh, I said that.
But your justification is,
Oh,
yeah, not so much.
so like half a point.
You get 1 from doing that. All right, last one. Write the electron configuration for zinc atom in the ground state. This is what we talked about today. Now, if you want to shortcut this because you want to do zinc, you can do the noble gas from the previous row to shortcut this, which is argon. And then you can go 4s2, 3d10. Okay? So if you want to shortcut that process, you can. Or if you're really hardcore, it's like, oh, I'd like to write up 1s2, 2s2. Okay? Kind of giving you that rhythm. And then on E, where it's got that last part, from which sublevel are electrons removed when the zinc atom is in the ground state is oxidized. Are you going to pull it from 3d10 or 4s2? 4s2, why? Which means they are further away from the, which means the coulombic forces are
Atomic radius.
weaker because you're divided by a bigger number, they'll be
Oh,
free.
I swear, the atomic radius on